Welcome to another lecture on numerical analysis. In this lecture, we will be studying Stirling's interpolation formula. Before this, we have studied formulas given by Newton's forward formula, Newton's backward interpolation formula, and Newton's divided difference formula. These formula, Newton's forward and Newton's backward formulas, were useful when we have to interpolate a value in the beginning or in the end of a given table. If we want to interpolate a value that is in the center of the table, Stirling's interpolation formula is the best formula to choose. This formula is used when the value to be interpolated lies near the center of the data table. This is the data table, and this is the table we have been drawing when we studied Newton's methods. Right, the formula is very simple. Y for any node that is in between any two given values, and preferably in the middle of the data table, around here or here, somewhere here or somewhere here. Right, so x naught can be here, or x naught can be here, near the center of the table. Right, it can be either here or it can be here. So let's work with this formula. Y naught is f of x naught is f of x b. The base value is the closest value, that is most of the times the central value. So if we have this x naught or this x naught, this central value will be the base value that we have been studying. The base value, we studied base value when we studied Newton's methods. Plus p is the difference here, x naught minus xb over difference. If this is and the formula works for uniform differences in x. For example, in this case we see there is a constant difference of 15 for all values of x. So p is x naught, this one, minus xb, the base value, divided by d, where d is any xn plus 1 minus xn, the difference in the x values, which is constant 15. So p is computed as x naught, the value of x for which we have to interpolate y, minus the base value, most of the times the central value, divided by d. So this is p, and we have this. For example, if this is xb, this is yb, the base y base, and we'll start with y base, and p is multiplied with the sum of the y up and del y up and del y down. This is del y up, this is del y down. So we start with this and up and down. So this is delta y underscore up. This is del y up. And this is delta y down. This is del y down, right? Right, so it's del y up, this is del y down. And as we proceed to the next term, that is p squared divided by 2 factorial, this is del squared y center. This is y center because up and down, and this is in the center. And then as you move to the third term, p times p squared minus 1 over 3 factorial, this is del cube y up plus del cube y down. This is del cube y up, del cube y down, plus p squared minus 1 over 4 factorial, and del to the fourth y center, this one. So this is how we proceed. We somehow try to interpolate the value using one upper and one lower term, and we move in this zigzag form. So this is the concept given by Stirling. So we start with the central value most of the times, and we somehow swing around the central value as we proceed in these terms. Right. So it seems quite simple, and we are given x naught is equal to 25. Here we are given x naught is equal to 25, this one. So this is the value of x for which we have to interpolate y. X naught is 25. We are given this value, x naught is equal to 25. Of course, the base value would be the closest value, and that is in the center 30. So this is xp. This value is xp. We have x naught is equal to 25. D is constant, as we have told earlier. This is the difference between the given values of x in the table, and that is 15 in this case, and it is constant throughout. And p is x naught minus xp, 25 minus 30 divided by this difference d. It comes out to be minus 1 over 3 in this case. So that's all. We have studied the formula, and we have completed the whole table. The table is the same as we have been doing for Newton's methods. This del y is computed this y minus this y, and this 0.24 is computed as this y minus this y. 0.21 is the difference between 0.707 minus 0.5, and this 0.16 is the difference between 0.86 is minus 0.7. We keep on going in the same way for del squared y, del cube y, and del to the 4y. And now we are all set to apply this formula, this given formula for this x naught, this xb, this d, and this p. So let's plug all these values in here. Y naught is f of the base, f of 25 is f of 30, f of x base is f of x naught, f of 30 is 0.5, plus p times this up plus this down divided by 2. P is minus 1 by 3, this up plus this down divided by 2, this one. And the next term is p squared over 2 factorial del squared by center. Del squared by center is minus 0.04. So p squared divided by p squared is 1 over 9, minus 1 over 3 squared is 1 over 9. Over 2 factorial by del squared by center is minus 0.04. And the next term is plus p into p squared minus 1 over 3 factorial del cube y up. Del cube y up is this, plus del cube y down, which is this minus 0.01. So let's plug all these values in here, and finally this one del to the 4 by center, and when we solve it, it comes out to be 0.4213. And we know this table is for sine of x, we already know that, and we have actually interpolated the value for theta is equal to 25 degrees. So it comes out to be 0.4213. We can verify our answer using any calculator, and we can use that to compute sine of 25. Sine of 25 using calculator, using any scientific calculator, sine of 25 comes out to be 0.422, which is very close, very close to the answer we have interpolated for sine of 25 using Stirling's interpolation method. So this method is some pretty good, pretty wonderful method to interpolate values for any y, given that the x or the y, they lie near the center of the table. Right. That's all for this lecture. Thank you.